Hey, so my name is Sveta and I'll continue my lectures about electricity in English. Yeah, and it's today its topic which is called internal resistance. Let's see what does it mean. And I have a special desk. I bought it for drawing, but it is not very good enough. Yeah, and I need it, put the cloth to vanish this previous text in water. Yeah, so I lost some time for that, and I believe that in future it cannot be used anymore. But for today, I hope it will be enough. Internal resistance. Of course, to understand this topic, you need to know the topic of a resistance itself. Yes, so this sign is usually for resistance. So it means, what does mean resistance? Resistance is something that not allowed current to go, or resists current to go through it. So yeah, that's why it's easy. So for current, for electrical charge, in fact, it's not so easy to come in through the material, even if its material is a conductor. Yeah, but we did not talk very deep about resistance itself. We will talk about the situation when we have a direct current power supply, direct current power supply. And usually when we have the ideal direct current power supply, it provides just voltage and that's it, that's cool. But in reality, it is not so. It has also its own internal resistance. So it has something inside its construction that do not allow current to easily come in through it, even if it's provide voltage and provides current for itself. And we usually mark it like this. We mark together these two elements, and we can call that it is a battery. So when we put a battery to the circuit, means a real battery that gives the opportunity all our electrical tools to work. This battery, yeah. So when we have a battery, we usually have a direct current power supply inside it, and we as well have internal resistance. Internal resistance usually is marked as R small. That's it. Yeah, and voltage, which is provided not just by the direct, which is provided by direct current power supply. When we have not just a part of circuit, for example, part of circuit sometimes is drawn by just points and the voltage between these points, yeah? So when we have this kind of circuit, we usually can say that here is worked Ohm's law. Ohm's law, yeah, where current is voltage divided by resistor. Yeah, the all resistance that we have in the circuit. That's it. Yeah, and that's absolutely right. When we have just a part of the circuit, it means we do not know where this voltage comes from. We don't know, do we have a direct current power supply, or do we have another kind of direct current voltage? It doesn't matter for us. So we can say that these 2 points are these 2 points. But between these 2 points is just voltage. That's it. So that's easy topic, and we can talk about it when we will consider resistors, just common resistance, in another lecture, I believe. So yeah, and now I try to raise this desk, yeah, one more time, and to talk more about another topic, yeah. So I mean, we continue, of course, with this one. I mean, but we will see a deeper circuit and how can we use Ohm's law in this situation, and how can we count, for example, a current that's coming through a circuit which consists of direct current power supply with internal resistance. That's it. You can see it's not very nice looking, but okay. So let's give it an opportunity to dry. You can see it's a very peaceful, very nice area here with a lot of dandelions. I love them so much, and yeah, and sun is shining, and of course it dries the desk very fast. Yeah, that's it. So we continue. For example, yeah, we can imagine a circuit which looks like this. Yeah, so we have a circuit where we have a direct current power supply, we have internal resistance R, yeah, we have a direct current power supply, and we have, for example, we have a voltmeter here, yeah, we have an ammeter here, yeah, and here we have, for example, a lamp. So here is a circuit for the torch lamp, and here is a switch, yeah. So yeah, it's a switch. So what is going on now? When we have such kind of voltage provided by direct current power supply, we called it's not voltage, just voltage. We called it EMF. We called it electromotive force. Motive force. This electromotive force also is in units of volts. So it's like an analog of voltage when we have the full circuit, the circuit with a battery. So yeah, and we can say that EMF, yeah, we have EMF is given for us with E, yeah, or it can be E, or it can be like epsilon, yeah, capital epsilon. That's it. Yeah, and so we try to understand to what needs in this circuit this EMF is given. So, and it seems that part of this voltage goes to exactly a lamp, yeah, which has its own resistance. But part of this voltage also goes to internal resistor, and it means that we have really work done by this electromotive force, which, for example, gives the torch lamp light only the voltage that goes to the resistor of the torch lamp. But the voltage that goes to a small r, internal resistance of the battery itself, it is lost voltage. So it is not used to provide a real work that we need. And we can consider such a formula. So the formula is that it's epsilon, yeah, it's electromotive force, and it goes, yeah, to the voltage which is under the Ohm's law, it's current multiple R, yeah, but it's also a current multiple R small, yeah. So it means here we have a voltage that provides real work that we need, and here we have like lost volts. So they are lost because they are not really goes to make the torch light, for example, yeah. And I will just write that it's a torch lamp circuit. That's it. So, and you can see that here, Yeah, so volts are just it's summarized. Yeah, and we can also consider this formula in some another way, and we can rearrange it to find a current. Yeah, so one moment, I will erase part of this circuit. I believe that not all, and because I think we can use this circuit to count some more interesting values. I mean, to use this circuit of torch lamp. Yeah. So yeah, and what we can say more. So when we want to find a current, and the direction of current is from plus to minus, and I want to remind you one more time that direction of current is the opposite direction of the electrons flow. So electrons are minuses that are going to plus, and the direction of current after Benjamin Franklin is called the opposite direction. So that's the direction of current. Yeah, and we wanted to know exactly this current. This current will be electromotive force divided by R plus R big. Yeah, and here you can see that it's the same formula, just rearranged. Very popular formula. That's important to know that here these are small, they are of this torch. It means the resistance that coming in series to the battery, or we can say that it's total. So it's total resistance. If we'll have more, if we have more, for example, lamps. Yeah, we can draw one more lamp here. For example, here. We'll need to find a total resistance for 2 of these lamps. That's it. Yeah, you can see it. Great. Yeah. Also, we can use this formula in such a way. It's also that's very interesting that in English or in the materials that I have found, they are differ from the materials that I used to. I mean the materials of Belarusian schools. And so we have this formula. Yeah, I write it one more time. So epsilon is current by R, and plus current by R small. Yeah, it's a rearranged formula as we have. This epsilon, yeah, or the voltage that's coming through from the direct current power supply, it is called EMF, electromotive force. Yeah, so this part, the voltage that goes to internal resistance, is called lost volts. Lost volts. And we have this part, and it has also its name. Its name is TPD. TPD means terminal. Terminal. Wow! I have forgotten. Terminal potential difference. Yeah, sure. So TPD. It's exactly this. This is TPD. Yeah, this is TPD. It's exactly the voltage that come into the torch lamps, and it's real voltage that do the job of making light, for example, in our case. And it has its own name. So it's terminal potential difference. Yeah, difference, not have place for it, but you can, you understood it. Yeah, that's it. And that's how we can count current, for example. Yeah, so I don't know, is it important for today exactly to resolve a task, but yeah, so the main theory you can see here. Yeah, okay. And I will erase this desk one more time. Try to erase it, we'll see. have a lot of levels of drawing here. Okay, yeah, you can see my progress. So without water it is impossible to erase it. I tried already and had no success. I think it's even easier to paint just on wood with calc, because it's easier to erase the text after it. But it's difficult to erase text on this desk, which gives this special opportunity. So that's crazy. That's crazy. Okay, we give it some time to dry. Yeah. What I want to tell more, that's interesting moment. We also have opportunity to investigate one kind of resistance that is called rheostat. And when we investigate rheostat and its dependence of voltage from the current, we can find the electromotive force of the battery as well of the internal resistance. And that's a very cool approach. I want to share it with you. It is dried. Yeah, it is dried, but it looks okay. So it is dried, and let's see what do we have. Yes, what can we do? How it is called? Rheostat, I believe. Yeah. So it's a resistance. We'll talk a little about this. A resistance with an arrow. It means that this resistance can be changed. Yeah. And for example, we are provided of the dependency. Yeah. So it's really that we can have a rheostat and can just use voltmeter and ammeter and see the dependency of the voltage. Yeah. In volts, for example, that depends from the current in amperes. Yeah. That's it. Let's draw very easy dependency. For example, here is 0.5, 1.5. Yeah, and here we will have 3 to 1. Yeah, for example, this dependency. So let's see what plot we can make for it. Yeah, so this methodics includes the graph, and we use graph to find electromotive force, this epsilon, this voltage that is provided from a battery, and we'll find the internal resistance. And here is voltage, here is current. Yeah, we can. Here is 0.5, for example, 1.5, yeah, and here is 1, 2, 3, so here is 3, 2, 1, yeah, that's it. So we began to draw points. So the here is 1 point, the next, and so of course that's approximately. So this methodics gives this approximate results. So it's results that comes from a real experiment. And what should we do next? The next we need to provide a line that describes the characteristics of these dots. Yeah, so this line is approximation of how the voltage can depend on the current. And that's interesting that here exactly where we'll have the cross, yeah, with the axis of voltage, and it should be, you can guess, it should be something about 4. Here is exactly the value of electromotive force, so it's 4 volts. And so this is electromotive force. We have found electromotive force now. That's a very nice approach, yeah. And also also, that's not all, we want to find the internal resistance here. How can we do that? We can also use the formula that we already used, where epsilon is r small plus r big. So what can we do here? Yeah, and here is our voltage. Yeah, so here is our voltage. So this one, yeah, you can see that. And you can see that we can have a formula for a linear plot, for a linear graph, and we can provide the dependency of V that depends on current E. How can we rearrange it? So V stays here and E goes there, so it will be minus RE plus epsilon. Exactly because of that, we can see when the current is zero, it means here when the current is zero, we have the situation when V is equal to epsilon. So it means that exactly this point, yes, that we have already drawn. Yeah, and we can find R small. How can we do that? We can use the values, yeah, of the table. For example, let's use the second one, the second pair, and we can put voltage as 2. You can see, yes, we can put current, so minus R current is 1 plus epsilon, which is 4. And from this equation we can find R small, and we can see how much should it be. It should be 2. Yeah, it should be 2 ohm. So you can see if it's 2, we multiply 2, 4 minus 2 is 2. Yeah, you can see that. So that's very, very nice. So here is a very interesting situation. And also we can see here that if to look at R small from another point of view, and to draw, for example, such a triangular here, it can be any triangular that is, how to say, any triangles that we can make between any 2 points, yeah? And we can see that this part is, yeah, it's like a delta V, we can say, and this part is delta I, yeah. And when we divide, yeah, just divide delta V to delta I, yeah, it will be 2 divided by 1, yeah. So we will have the tangent of this angle. For example, it's angle alpha angle, yeah. And this tangent is also 2. So this tangent is connected to this R small. That's also a variant how we can find this small r. Yeah, that's it. Okay, so for today I believe that's all. Yeah, so I'm happy to share my knowledge with you. I'm happy that these desks gave me the opportunity to raise it, to redraw it, because that was a big problem for myself. I'm happy that I'm staying on the countryside and you can see this so beautiful field, yeah. And the physics is cool, so learn the laws of nature and I can help with it. And if you like my lectures, you can support me and give me money, food, share some ideas with me, give me a cup of coffee, yeah, and so on. I'm open to the opportunities and the collaboration, yeah. So okay, goodbye for today.